Welcome back, my dear students. So in the previous video, we have discussed about self-adjoint operator, unitary operator, and normal operator. Now, similar definitions can be used in terms of the matrix algebra. Okay, for that, let's consider the space Cn. Consider the space Cn. Cn means set of all n tuples, theta 1, theta 2, etc., theta n, where each theta I is a complex number. Now, define an inner product in this space Cn as if x and y element of Cn, then inner product xy should be equal to x transpose y conjugate. Here conjugate is actually meaning the usual conjugate of the complex number. If y is actually eta 1, eta 2, etc., eta n, where y is element of Cn, y conjugate means eta 1 conjugate, eta 2 conjugate, etc., eta n conjugate. Now, x transpose means if you write x as theta 1, theta 2, etc., theta n, this is actually, it can be interpreted as a row matrix form. Then its transpose is actually x transpose. So this is actually the inner product which is defined on Cn. Now let T be any arbitrary linear transformation from Cn onto Cn is linear. Since Cn is a finite dimensional inner product space, it has a dimension n or 2n with respect to the underneath field. So T is a linear map which is defined on a finite dimensional space. So clearly T is bounded because every linear map which is defined on a finite dimensional space is actually bounded, which we have already established. Now T can be interpreted as a matrix. So T can be interpreted in terms of a matrix. Let's say A, which is true because every linear transformation from a finite dimensional space onto another finite dimensional space has a matrix form. Here, this should be an n by n matrix. Let that matrix be A. Associated with every bounded linear transformation, we have its adjoint T star, which is also a map from Cn onto Cn, and this can be also interpreted in terms of a matrix, let's say B. Since T is linear and bounded, its self-adjoint operator, so its adjoint operator, Hilbert adjoint operator, T star is also linear as well as bounded. So T is actually represented by the matrix A, and T star is actually represented by the matrix B, which means that Tx is actually Ax and T star Y is actually By. This is actually the meaning. Now, we have to somehow relate this T and T star with respect to these matrices A and B. Since T star is actually the Hilbert adjoint operator of T, by definition, it should satisfy inner product Txy should be equal to inner product x T star y. Okay, where x and y element of Cn. Now, by definition, Tx is actually Ax and inner product xy can be written as x transpose y conjugate. So inner product Txy can be written as, this implies Tx is actually Ax. So Ax the whole transpose y conjugate. Similarly, T star y is actually By because B is the matrix associated with T star. Inner product x T star y can be written as x transpose By the whole conjugate. Now we have xy the whole transpose is equal to y transpose x transpose, and xy the whole conjugate is x conjugate y conjugate. So using this we can write this as x transpose A transpose y conjugate, which is equal to x transpose B conjugate y conjugate. So this is true for all x comma y element of Cn. So if T has a matrix, T is a boundary linear operator and has associated matrix A, and T star is the adjoint Hilbert adjoint operator of T, which is represented by a matrix B, then it should satisfy at x transpose A transpose y conjugate should be equal to x transpose B conjugate y conjugate for all xy element of Cn. So from this we can clearly write this as A transpose is equal to B conjugate, or in other words, A transpose the whole transpose should be equal to B conjugate the whole transpose. A transpose the whole transpose is A, or A should be equal to B conjugate transpose. Or in other words, if A is the matrix associated with a bounded linear operator T and B is the matrix associated with its Hilbert adjoint operator, then A and B are related by the relation A is equal to B conjugate transpose. So this is the matrix relation associated with an operator and its Hilbert adjoint operator, where A is actually the matrix associated with T and B is the matrix associated with T star. Since we have this relation, using this relation, we can clearly state the definition of unitary operator, self-adjoint operator, and normal operator. Recall the definitions of matrices. So a matrix is called Hermitian. A matrix A is called Hermitian if A is equal to A conjugate transpose. And it is said to be skew Hermitian if A is equal to or minus A conjugate transpose. And it is said to be unitary if A inverse is equal to A conjugate transpose. A inverse. And it is normal if A times A conjugate transpose should be equal to A conjugate transpose times A. So this is the definition of various classes of matrix. Now, an operator T is unitary if the associated matrix A is unitary. and it is self-adjoint if A is self-adjoint, and it is normal if the associated matrix A is normal. So we have successfully related the matrix of A and its Hilbert adjoint operator. From this, we can write A is equal to B conjugate transpose, or if we take the transpose, A transpose is equal to B conjugate, or B is equal to A conjugate transpose. It can be actually interchanged. Okay. So the matrix of the Hilbert adjoint operator T star and the matrix of T has been related using the relation B is equal to A conjugate transpose. Now, an operator is said to be unitary or self-adjoint. Let's start with self-adjoint. T is self-adjoint means T star is equal to T. T star, which means that its associated matrix, the associated matrix of B should be equal to A, where B should be equal to A conjugate transpose. That is, A conjugate transpose is equal to A. This is the definition of self-adjoint. Now, this condition satisfies if and only if A is Hermitian. So, we can conclude that T is self-adjoint if and only if A is Hermitian. Now, similarly, T is unitary if T star is equal to T inverse, and the associated inverse of T is actually A inverse. So, A inverse is equal to B. Here B is actually A conjugate transpose. That is, A inverse is equal to A conjugate transpose, which is the definition of unitary matrix, or A is unitary. So an operator, bounded linear operator, T is unitary if and only if its associated matrix is actually unitary. And thirdly, T is normal if T star is equal to T star T, which implies associated matrix AB should be equal to BA. Here B is equal to A conjugate transpose, that is A conjugate transpose should be equal to A conjugate transpose A, which is the definition of normal matrix. So T is normal if and only if A is normal. So using the matrix, we can define self-adjointness and unitary operator and normal operator. An operator T is self-adjoint if and only if its associated matrix A is Hermitian, and an operator T is unitary if and only if its associated matrix A is unitary, and T is normal if the associated matrix A is normal, whenever T is defined on the complex space. But the similar definition can be interpreted in terms of the real matrices as well. In the case of real matrices, A conjugate, so if T is defined on, let's say, Rn onto Rn, then A conjugate is actually A, because conjugate of a real number is a real number itself. It doesn't have imaginary part. Then A conjugate transpose should be equal to A transpose. So if T is defined on the real space, its B is actually equal to A conjugate transpose, which is actually equal to A transpose. So on the real space, so if A is real square matrix, T is self-adjoint, if and only if A is Hermitian, meaning A is equal to A conjugate transpose, which is equal to A transpose, because A conjugate transpose is equal to A transpose in the case of real matrix. And A is equal to A transpose, meaning the matrix is actually symmetric. So in the case of real square matrix, T is self-adjoint if and only if A is symmetric. Similarly, T is unitary if and only if A inverse is equal to A conjugate transpose, or in the case of real matrix, A conjugate transpose is A transpose, or A inverse is equal to A transpose. A inverse is equal to A transpose, meaning A is orthogonal, which is the definition of orthogonal matrix. So in the case of real square matrix, T is unitary if and only if A is actually unitary. So every bounded linear operator, its properties such as self-adjointness, unitary and normal operation can be interpreted in terms of the matrix as well. So in the case of complex matrix, an operator T is said to be self-adjoint if and only if A is Hermitian, associated matrix A is Hermitian, if T is actually unitary if the associated matrix is unitary, and T is normal if the associated matrix is normal. In the case of real square matrix, if the associated matrix of T is a real square matrix, T is self-adjoint if and only if A is symmetric, and T is unitary if and only if A is orthogonal. So this is the definition. So every operator on a finite dimension space, its properties can be interpreted in terms of the matrix as well. Thank you.